Ladies and gentlemen, please welcome Propulsion and Energy Executive Steering Committee member and retired Vice President of Sandia National Laboratories, Rick Stuhlen.
Good morning, everybody. Welcome to day 2 of the forum. It's good to see you here. In fact, the numbers I think I heard this morning are we have something like over 1,300 folks from across the United States and the world actually here today. Aside from the weather, the conference is in a spectacular location. I don't know how many of you had a little bit of a challenge yesterday getting in or over the weekend, but I'll tell you this location is just amazing. I grew up on the Great Lakes up in northern Michigan. So to come back and see the Great Lakes again is really a treat for me. And of course, walking in and seeing that wind turbine out there certainly sets the stage for this being a joint energy and propulsion conference. Great to see that. As all these conferences are, this is a great opportunity, I know you know this, to meet colleagues, to reconnect, network, broaden the network, and actually it's this kind of thing that creates some of the ideas that shape the future. So I encourage you to reach out to your colleagues and others at many of these different sessions and look for some of those new connections. This theme of energy and propulsion provides an opportunity to do just that. Day 1, so we had a great day yesterday from seeing so many young professionals at the Rising Leaders Town Hall last night. Some of you, I hope, got a chance to do that. In hearing that inspiring vision for the community's future, seeing the crowd, hearing the buzz at the exposition reception, and hearing all the side conversations in the hallway. I mean, it was a great day. I trust that many of you experienced all of that. Don't forget that tonight we have another Rising Leaders event, which is the Brand Yourself session. That starts at 1900 hours. I encourage you to come to that as well. I also want to offer yet another round of thanks to the sponsors of AIAA Propulsion and Energy 2014. Special thanks to our executive sponsors, GE, NASA, Lockheed Martin Corporation, as well as to our additional sponsors, Dunmore Corporation, IEEE, Incos, Jacobs, Ohio Aerospace Institute, Cerro Lobo, Southwest Research Institute, and United Launch Alliance. Wow, that's a mouthful. And also special thanks to our media sponsor, Space News. Just one housekeeping item as we get into the Q&A. There are mics in the aisles. Many of these sessions, this one included, will be streamed. And it's nice for those who are online to be able to hear both the questions and the conversation that ensues. So please use the mics as we get into that part of the discussion. With that in mind, I'd like to turn now to introducing Dr. Al Romig, close friend of mine, many years. Many of you also probably know Al since he's one of those individuals that loves to connect. He has basically 2 speeds, off and full speed. And those of you who know Al will understand that comment. Al got his degree at Lehigh University. He's currently at Lockheed Martin. He's the Vice President for Engineering and Advanced Systems, Aeronautics, and is having a fabulous time there, I know. Al is one of those individuals who's not only a fantastic leader, but also mentor and friend for many. He has the degree from Lehigh is in material science, so I'll tell you, if you ever get into a conversation around materials, watch out. He knows his stuff and can help, in fact, solve many, many problems because of that background. We also, I think you may have noticed that we have Al on tap for some additional talks, one this evening which will be on the history of the Skunk Works. I'm particularly looking forward to that and hope that some of you will be able to join me as well. So with no further ado, let me turn the mic over to Dr. Al Romig. Al?
Thank you, Rick. Well, good morning, everyone. Hopefully, you'll be able to understand this. I noticed back there's a pretty bad echo in the room, so maybe I'll slow down just 1 speed so that the echo has a chance to die away before I utter the next word. Well, when Rick asked me to talk with you all today, about energy and aerospace and where the two will eventually come together in the future and what that means to us as an industry and as a discipline, one of the questions you would ask is, over what time horizon are you asking that question? Is it 10 years? Is it 20 years? Is it beyond? Well, what we'll have to say today is pretty much about 20 years and beyond. But I'll also add the comment that whenever someone asks you a question about what's the time horizon for an engineering system, there's a certain ambiguity in that. You know, the proof of principle of something might happen in, say, a 10-year period. But by the time it actually is introduced into a fleet, whether it's commercial, military, or whatever, could well be 30 years. So in this case, I'm thinking more about things where even the very basic science of it all could be 20 years into the future or beyond. And that's not to say that I won't make some comments about more traditional things with regards to energy, but the focus here is really going to be at times beyond that. I know you've already had some lectures this week where people have talked about some of the new things that are happening with hybrid power, et cetera. We also know where propulsion has gone over the course of the last few decades. I'll make a few comments there, but once again, I want to try to stick to a time horizon that's a bit beyond that. So if I think about trying to lay out a conversation like this, and I really do want this to turn into a conversation at some point, because there's nothing here that's set in stone as gospel. But what are the drivers that make us worry about energy and how it impacts aviation and transportation, be it military or be it commercial? What are some of the revolutionary things or evolutionary things? I think I've already mentioned a few that I would consider evolutionary, but there are likely some that are out there revolutionary. Some of which, when I bring them up, will no doubt really stretch your mind. And you might say, what's Al been smoking this morning in order to even bring a topic like this up? But I'll show you some examples of what can actually happen over relatively modest periods of time, where things absolutely unbelievable happen in a period of only a few decades, which is not really that long. What might be some of the future approaches to those revolutions and evolutionary developments? Energy efficiency. Are there some really off-the-wall things that might happen, say involving fusion energy or beyond? Are there other ways to generate energy or source it that are right now just merely theoretical, but someday could turn into a real system? Are there things really like a warp drive, for example? There certainly aren't today, but I don't think anyone in this room would predict that there won't be by the year 2114. There might well be. What we don't know. A lot of things we don't know about the universe yet and how that might impact what we do with energy. And then some examples that say, trying to think in a linear fashion by projecting backwards and imagining what will happen in the future is really not a very good predictor of where things are going in the future. So let's take a tour down some of these really off-the-wall ideas and see where they're going. Well, what are some of the things that are driving us? Well, first off, we know there's increasing energy demands. You've all seen the predictions for what's going to happen with air travel commercially, whether it's cargo or actually passenger transport over the course of the next 2 decades. The predictions of growth are just amazing. And there's no doubt they're going to come true. Just look at the order books that Boeing and Airbus have for aircraft going into the future. And you can clearly project more and more the world wants to travel. The energy demand is going through the roof. Despite the fact that aircraft and propulsion are getting more efficient, the demand is rising even faster. What about cost? Well, it now seems that there maybe is a more accessible fuel than we thought there was. There's always this interesting balance when you talk about supplies of hydrocarbon fuel, where people talk about what can be extracted, what's conventionally available. Well, the definition of what's conventionally available changes over time. And a lot of the oil that we produce today that we think of as being more or less conventional would have been viewed as unconventional some number of years ago. Of course, the one that gets the most press right now are oil and gas that come from shale or other kinds of tight formations. But it's clear that the quantity of hydrocarbon fuels is larger than we at one time thought, at least fuels that were accessible. But if you think about it, we're left with 2 dilemmas that drive affordability. Either the reserves are in places in the world that are not particularly stable, and that drives cost and security or maybe transportation costs. Or it are things that we used to consider more or less non-conventional, and the cost of extracting them are a lot higher than just sinking a hole down, a few thousand feet into the sand and pumping out the oil. It costs a lot of money to extract oil from tar sands and from shale and so forth. What about the impact of climate change? I think there's a lot of data that clearly suggests that climate may be changing without even getting into the debate for where it may come from. But nevertheless, there are issues out there and people wanting to cover their bets and say, do we need to do something about what we emit into the atmosphere for whatever reason that we think may or may not be causing a climate to change? Globalization. Right? The world has clearly become more and more global all the time. Right now, there's no doubt that Boeing and Airbus dominate the commercial aircraft market. But we can see Bombardier and Embraer on the rise, Comac in China. What will the stable of aircraft manufacturers for commercial purposes look like 50 years from now? How many players will there be? Will some of the players that are now there today be gone or be absorbed into somebody else? Who knows? What about in the realm of the military? Well, I think global military spending is probably going down. Could you see more consolidations? You might. There's no doubt that a lot of other parts of the world have recognized that there's potential huge markets available with foreign military sales. You see that amongst a lot of our allies who are now beginning to try to sell into the same markets that traditionally somebody like the US or maybe the Russians or in some case the English and French have tried to sell into. But globalization happening from every which dimension you can possibly think of. Well, government policies on a cross of all those above, right? How are they going to impact things? The government can do things, whether it's a government, meaning the US, or something in Europe, or some kind of an international agreement that limits, who knows, whatever it might be, a carbon tax, for example, for emission from engines. The Europeans already on that path. Where will the US end up in that? Who knows? But there are policy changes that could drive a lot of these things. I've talked already about commercial traffic increases as they tie to the growing demands on energy, right? And finally, once again, I mentioned it, but national security issues, where do those all go? It's interesting, without getting into a dialogue of historians, that you could argue that every major conflict the world has ever seen at the end of the day is driven over the availability of resources. If you look at World War II and you look at the Japanese desire to have oil, et cetera, from South Asia, potential interference from what the US Navy might have been doing to make it difficult to get that oil. In Germany, driving towards Romanian oil fields, Middle Eastern oil fields through North Africa, et cetera. But go back and look in history, and virtually every major conflict, somewhere in there, even if it's around land, it's somehow tied to resources, whether it's oil, whether it was food, whether it was water, wherever it might be. So those demands are always going to continue to exist, and I think will be a driver in all of this as well. But there's no doubt that you look at all these things, the availability of and the use of energy are going to be important as we move forward. Well, I think some people would argue that the long pole in the tent of aviation efficiency is in the area of propulsion. And just think about what's happened over a period of just, a handful of years. From the time of the first Wright brothers engines in the early 1900s, a little bit more than 100 years ago, and what engines looked like then. And by the time we got to the immediate post-World War II days, with highly efficient, high horsepower, low weight, turbocharged piston engines flying in things like DC-7s and Super Constellations. Of course, that's a Super Connie. What would you expect a guy from Lockheed to show on the screen? But nevertheless, real advances in what we could consider rather traditional piston engines. Well, what happened after that? Well, at the same time, rocket engines. Solid rocket engines go all the way back to the time of the Chinese, 1,000 years ago. But think about liquid-fueled rockets. Goddard had his first flights in Massachusetts, then later in the middle of New Mexico in the 1920s. And by the time we got to the 1980s, the engines that were driving things like the shuttle, so a mere passage of 60 years or less, 55 years, right? And it's interesting to watch what's happened to rocket engine technology now. The traditional chemical energy, I think you've seen all the debate in the news about, well, if we can't get the 180 from the Russians, we want to start development and rebuilding of a line here in the US. We want to try to come up with a more modern version, for example, Rocketdyne, Aerojet Rocketdyne with the engine that drove the shuttle for our future launch purposes. You might argue that conventional liquid-fueled rockets are relatively mature. Perhaps they are. Maybe there's other things that might appear on the horizon. But nevertheless, remarkable progress in a period of only 50 years. And then finally, what about the jet engine? Right? The first jet engine flew in a Hinkle 178 in 1939. And by the time we got into World War II, the Me-262 first flew in 1943 and actually entered combat service in 1942. 1944, right? And it was really a quite modern engine, axial flow engine. It suffered a lot from materials, only literally a few hours between every overhaul cycle because it was just pushing the materials inside to such a great limit. But look at where we are today. If you look at a modern engine, the weight and the thrust that engine produces, and I just think about all the advances that I've seen over the course of my lifetime, and I think you as well. Whether you're talking about the mechanics of it, things like going to geared fans, et cetera, in some of the most recent versions, or things happening with materials from single crystal alloy blades. When I was a graduate student back in the 1970s, excuse me. Boy, did I make myself old. In the 1970s, we were going to have ceramic parts in jet engines and intermetallics. Well, finally, here we are 40 years later, and the first ceramic parts, non-rotating, are beginning to appear in the prototype engines coming out of the engine manufacturers. And so the whole drive towards trying to use ceramics or intermetallics in some cases was to drive the temperatures up and get more thermodynamic efficiency out of it. So whether we're talking about materials, we're talking about cooling, putting cooling channels inside of blades, for example, geared fans. A lot has happened over the length of time, even the fan jet itself compared to a turbojet, that's done things over the course of the last few decades to greatly increase fuel economy. And every time the engine manufacturers come along with the next generation, it's another 15% or whatever the number happens to be for each cycle of improved efficiency in engines. Well, how far can we push that? And we'll see where it goes. Novel things, whether or not this ends up ever having commercial applications, I think would be debatable. But you can look at the JSF, the B model for the Marine Corps, that takes 90,000 horsepower off the shaft and drives a lift fan that's mounted right behind the cockpit. That's a pretty interesting feat in mechanical engineering. If you talk to some of the engineers that actually designed that transmission and gearbox at what was then Allison and now Rolls-Royce, it's really a pretty remarkable piece of engineering that you can reliably build a box of gears that can take the kind of stresses and loads, et cetera, that one in particular does. But if you look at the migration from 1904 or 1903 and the engines that belong to the Wright brothers to a lift fan or one of the highly efficient engines today, only a mere 100 years later, it's really pretty remarkable. I think if the Wright brothers saw propulsion today, they would have been totally shocked by the rate at which it's all advanced and where we've been able to go with it. And this game is not over. There's a lot more that can happen. And I think it's one of the areas where some of the things will happen relatively near term. And I know you've talked about those earlier this week. The notions of distributed fans and hybrid engines and electrical power and the whole debate about, golly gee, a charged battery, a lithium ion battery, a charged and an uncharged one weigh about the same. So you're not gaining efficiency by losing weight as you burn off energy from that fuel supply. But nevertheless, lots of ideas that are out there that I think may have some legs. The idea of moving towards a more electric jet. Now that doesn't necessarily mean you're going to have the pure electric propulsion in it. But just like in a modern automobile, there's more and more things that are done electrically and fewer things that are done, say, hydraulically, like they were in the past. How far can that game go? What does that do to the thermal loads inside of an airplane? Right now, we're already about at the limit for what you can do in an airplane to handle the heat that's generated just by the mission systems and so forth that's in it. Right now, we use the fuel as a heat sink, but the thermos bottle is just about out of capacity to hold more heat. So as we continue to make some larger and larger advances, what will that do to drive the needs to do something with how we handle thermal energy? I think a lot of you have heard dialogue about, are we going to get to the point where we will be able to mount, perhaps for self-defensive purposes, lasers in airplanes? Well, getting it small to put in an airplane, getting enough power to make it useful as a self-defense weapon, that's one set of challenges. But if you take a look at the size of the generators that are needed to do that, they generate an awful lot of heat. What are you going to do with it? Well, those are all problems that need to be solved. So there's an issue of getting energy to do things that you want, but then there's also the issue of the efficiency and the energy that you don't want that you've got to get rid of as you get and move towards the end. So what's going to be next beyond that? Well, people have stretched this for a long time. This actually is a picture of Hull Hillard, one of our folks, back in 1939, when Kelly Johnson and others began working on internal dollars on an axial flow jet engine up in Burbank, California. By the time we came along to build the XP-80, we used the British engine. which was a centrifugal engine, but nevertheless, we did in fact use that one. But people oftentimes think about the work that was happening in Germany or in Britain around jet engines, but there were things happening here in the US as well. A little bit behind, I think, probably at the time, although you could argue that a design like that was pretty much cutting edge at the time that it was done. But Lockheed has shown a willingness over its entire life to be willing to invest money in things of its own that go beyond that. And so I think, like a lot of other companies, the notion oftentimes is with a small idea, when quite frankly, when it's still at a relatively immature state, the amount of dollars you have to spend to explore it is not large. But trying to see if there's ever really a there with some of these new things and what that might mean in terms of then developmental dollars that might require larger investments of funds to the benefit of the entire industry that would come from a DARPA or an AFRL or an ONR or a NASA, whatever the source might be. But so just an example that companies will spend their own money up front, although they oftentimes in our current business model for this industry will use government help to carry it over the valley of death. So where do we think this might all go as we go into the future? Well, there's a lot of things that could happen. Alternative fuels, electrical power sources, I mentioned that one before, energy harvesting, distributed propulsion, energy efficiency, and revolutionary energy sources and storage. Well, think about alternative fuels, right? If you take a look at jet fuel, it's gone through a lot of evolutionary changes over the course of the last 50 years. Trying to make it safer, make it burn more efficiently, make it generate less pollutants as it burns, et cetera. People have looked at hydrogen, for example, in airplanes for a long time. And there have been examples of people having flown one of the engines on a larger airplane with hydrogen or with methane. Both of those are alternative. But it's an interesting challenge. As far back as the late 1950s, if you think back to the days of the heyday of the U-2 in the 1950s, the whole idea behind the U-2 is to be able to fly high enough to be able to be immune to integrated air defenses and be able to watch what the other guys were doing. Well, it became obvious at some point that altitude alone wasn't enough, so we had to go fast. And in the late 1950s, no one thought you could push a hydrocarbon engine-powered airplane to speeds of Mach 3 or beyond by using hydrocarbon fuels. And so if you go back and look at one of the earlier precursors to what's now known as the SR-71, that originally was done under a concept of an airplane that was called suntan. The interesting thing about that was meant to be hydrogen powered, meant to fly at 100,000 feet, meant to fly in excess of Mach 2.5. And at the time, no one thought that you could actually do that with a hydrocarbon fuel, so hence hydrogen. And if you go back and you look in the history of that program, you'll see that Kelly Johnson was in fact the program manager to do that. But they actually took one of our best engineers at the time, and actually eventually Kelly's successor, Ben Rich, to figure out how you can actually build a plant to make hydrogen and put the infrastructure together to power the airplane. So the source of the fuel and how you handled the fuel became as much of an engineering challenge as the airplane itself. And quite frankly, if you take a look at hydrogen as a fuel, whether it's in automobiles or it's in aircraft, the whole issue of generating the hydrogen isn't so much of a problem. I guess you can crack methane, but if you do that, you still end up with a CO2 problem. But it's probably easier to make the hydrogen than it is to really figure out what to do with it once you've made it. You know, I know Rick in his earlier when he was still making an honest living before he retired. I've known Rick for 35 years, so I can say things like that. But Rick ran a program for us, for the DOE, that looked at advanced solid-state storage of hydrogen. That's always been the real nemesis for hydrogen as a fuel, is how you store it. Compress it, liquefy it, find a solid in which it can be dissolved at a higher density per unit volume and weight than you could, say, as a liquid, et cetera. But it's always really been a challenge. And eventually, by the way, suntan was canceled. And the principal reason it was canceled was around the cost that would have been associated with making the hydrogen and figuring out how to store it, building a supply chain for it to get it around the world to let the airplane fly. Back to the drawing board, and eventually figured out how to get a hydrocarbon fuel to work in a turbo ramjet and to produce the SR-71. Right? There's a lot of work happening now in the area of methane for fuel. Now, methane presents some challenges as well. Do you want to compress it? Do you want to try to liquefy it? You carry cryofuel in the wing of a commercial airliner we'll see. Methane doesn't have as much energy per unit volume as a jet fuel does, so it does things to the range, et cetera. But nevertheless, given the vast availability of methane with fracking, do we need to revisit that as a fuel? Or do we just want to do a gas to liquids process and turn methane into more conventional jet fuel and use it that way? So whether it's a matter of something really out of the box like hydrogen, maybe a little bit less out of the box with methane, or whether it's some other source of hydrocarbon fuel, whether it's a gas to liquids out of methane, a gas to liquids out of biomass, or whatever it might be, but a whole variety of things from less radical, being hydrocarbon based, slightly more radical with methane, to eventually hydrogen. And then maybe beyond that, as I said, who knows what could eventually happen with electrical power, or even some other really remarkable things. The idea of nuclear propulsion, which has been around for a long time, I'll say a few words about that again and whether or not it may come back. Electrical power sources. Well, there's a lot of things that can happen off of that. You know, as I made the comment about the large lift fan that's on the F-35, the B model, there's no reason you couldn't hook that drive shaft, that turbine shaft, up to a generator to do all kinds of things with it. You could build a hybrid, as we talked about before, where in some modes you're drawing power off of a battery pack, running engines to drive fans. In other flight modes, you're letting the fans just freewheel, taking the energy back and putting energy back into the batteries. Those things all, I think, are possible. One of the guys that works for us, a young man by the name of Pete Buck, building an electric airplane at home in his garage, which he plans to fly. So, brave man, I suppose. But nevertheless, there are small private airplanes that are battery powered. It's interesting, though, when you talk about battery powered vehicles of any kind, and a good friend of mine who just recently left General Motors and is now on the faculty at University of Michigan, Alan Taub, some of you may know him. You know, the comment that he would make about electric propulsion, albeit in cars, it doesn't really matter, is if you think about a car, an electrical car that has a range with fully charged batteries of, say, 100 miles. Well, that might sound like a lot for an electric-powered car, but think about it. If you got into your car in your garage and it had about a third of a tank of gas in it, which would give you a range of around 100 miles, what's the first thing you'd probably do? Go put gas in it, right? So, you know, just because the needle says full, you got to think about what that full actually means. You know, and if you run out of gas by the side of the road, that's something you can more or less do something about, you know, but if your electric car quits, you can't just go dump a gallon of gas in it and go another handful of miles. So lots of challenges in terms of the utilization of electrical power. Energy harvesting. I made the comment earlier about all the excess heat that's generated in lots of places. Well, there have been lots of schemes that have been proposed to extract that energy and do something useful with it. Everything from running a Rankine cycle, basically refrigeration cycle, and drawing energy off of exhaust gases to do something with it. Thermoelectric generators to try to generate power. Just using the heat completely to, you know, with a hot air flow, if you can get some bleed air to drive it over something to cool it. Lots of places where you might be able to harvest energy off of a system, none of which have proved out to be very efficient. We actually did look at the possibility of extracting energy off of a Rankine cycle in the exhaust at one time, but it just doesn't close as an engineering case. The thermodynamics are just not really quite there. But there's a lot of free energy there. It'd be nice if we could find a way to somehow use it. And I would even make an argument that to some extent, that's what was done in the in the 40s and 50s with some of the compound turbocharged engines, piston engines that were used, where there were three-stage turbos that were extracted energy out of the exhaust to drive all kinds of things. So they didn't have to drive energy off of the crankshaft and could use these other sources of power for electrical and moving oil or whatever else it might be. But certainly opportunities, I think, there. Distributed propulsion. A lot of folks are talking about that. There's a way you can use one turbine to drive potentially multiple engines, et cetera. Schematics for that have been around for years, for example. Energy efficiency, right? Bigger fans. That's where you get to the notion of maybe multiple fans off of things. What about perhaps where you put things on the wing? I'll show you an example of that later. Does that do something to how the aircraft might fly with regards to its efficiency? And then finally, some things that are going to be really out of the box that I think none of us are ever going to be around to see. Well, some of the younger folks in the audience might be. I suspect that some of us won't be around by the time some of these things could potentially be realized. Well, this is something that some of our folks worked on over the course of the last few years, and as a matter of fact, a paper that the group gave at SciTech last January received a Best Paper Award for the work that they had done on it. But it's a so-called a hybrid wing body, and there's a couple of things about a design like this that I think really, we believe, for example, if it was a C-17 size airplane, this particular design would be about 70% more fuel efficient. And that happens actually for a couple of reasons. One is because of the CFD models that we have these days, augmented, of course, by the proper use of wind tunnel tests, the wing on that airplane and the airflow on that airplane is absolutely optimized for maximum efficiency. Maximum lift over drag. It has a tail on the airplane. It's not intended to be stealthy per se. So you get a lot of lateral stability with a vertical tail that you wouldn't get in a true flying wing. So absolutely optimized geometry for the airplane from an aerodynamic perspective. Now, it does create some interesting challenges. I guess I'll point in this side. You know, you have to worry about how you try to utilize space in the inside of that airplane. If it's going to go through pressurization cycles, you're going to want to have a tube inside in order to handle the hoop stresses a little bit better. Leaves perhaps some dead space. You got to be clever about how you store fuel or cargo or whatever else it might be that's in a shape like that, but nevertheless, absolutely optimized shape of the airplane. Second thing you'll notice is the engines on the back, right? We actually have a schematic of this, one that uses unducted rotors and one that's just large encased fans like this. But what you need to notice about that is look at how large those engines are and how large the fans are. Huge, done for efficiency. But as engines get bigger and bigger and bigger, it begins to create a problem. How much room is there between the wing and the ground, right? The engine gets big enough, pretty soon you're going to have to start making landing gears taller. That might create an issue with it. Besides the fact that I think a lot of you have seen the photographs of little vortices forming in front of an engine and stuff getting sucked up off the runway and ingested into the engine, potentially doing damage. So larger and larger fans underneath wings of airplanes eventually become problematic. Put the engine on top. Honda Jet already uses a design similar to this. But one of the things that we found out by doing this is by having the inlet air come in over the top of the wing, it ends up giving you about a 5% advantage in lift by having that flow over the top of the wing. So you get sort of an extra bonus out of it as well. So absolutely optimized with respect to the engine. So that's over to our friends at Pratt and GE and Rolls to sort of figure out that problem. And then it's the airframes. And so whether it's a Lockheed design, Boeing's working on similar things, et cetera, ways that you can absolutely try to optimize the shape of the airplane for aerodynamic efficiency. This stuff is all relatively near term. Now go back and think about my comment about the time horizon for things, right? Conceptually, this is already done. There's nothing really radical there. Now the problem becomes the engineering, right? Building the airplane and building the engines. But till something like that would ever enter the fleet is certainly no sooner than, say, 2030. So in terms of fleet introduction, that's already 15 years away. But in terms of being able to appreciate the technology that's in it, that time is already here. Right? So where do we go from this point? Let's get a little bit wilder. Well, let's look at one that Lockheed has worked on and off at a very, very low level. And whether it ever works, who knows? It's something where I think the odds of it working are probably not very large, but if it does, the impact would be huge. If you think about nuclear fusion, we've known how to create nuclear fusion since the first thermonuclear weapon was detonated back in the early 1950s. And we've been trying to control it ever since. And there's been a whole variety of schemes that have been tried that are inertial confinement schemes of sorts, that are magnetic confinement schemes. And if you take a look at the whole litany of things that have been done, every one of the approaches has things about it that look really appealing, but then there's some fatal flaw. And so in a nutshell, without getting into all the detail here, is there some way to learn from all of those things and come up with a design that gets us around some of those limitations and potentially gives you the ability to build something in a reactor that's, maybe the size of this, 2/3 of the size of this stage cube, and actually use it to fly a large airplane, perhaps. But if you could ever accomplish that, imagine, I made the comment earlier about energy driving most global conflict. Not a new concept, you've probably all heard it before, but all of a sudden you have a limitless, quote unquote, supply of energy with fusion. that changes the entire global equation on competition for resources over energy, one way or the other. Now, if things like this ever work, unfortunately, airplanes are probably the last place that you'd see them because they are relatively large and would require a large airplane. But the notion of a reactor like that in a ship or in a remote ground station, whether it's a military base or a remote mining village or whatever it might be, is really quite appealing. And I ask you to think back to the days of fission reactors. And today, when you talk about a nuclear-powered vessel in the U.S. Navy, it's only one of two things. It's either a nuclear submarine or an aircraft carrier. But if you think back into the 50s and early 60s, there were nuclear-powered ships of all sorts that were built. Frigates, hospital ships, freighters that were all built with nuclear power. Later on, they decided that there's a little bit of a hassle in terms of fuel changes, et cetera. Fission creates a lot of issues when you use it in the Navy. And so they picked the two classes of vessels that were the benefits of having nuclear power far exceed the liability of having it. But imagine if somehow you could get around a lot of the liability of the waste, et cetera, and that's what you have to do to decontaminate a ship at the end of its lifetime and replace it with some other form of nuclear power. It would be absolutely revolutionary. So maybe you'll be able to demonstrate a reactor by the year 2030, maybe, right? But suppose you did demonstrate it by 2030. From the time you first got one to run and break even in a laboratory in 2030 until you saw it actually on board a ship is probably 10 years beyond that. On an airplane, it's probably 20 years beyond that. So the concept exists today. Maybe demonstrate the engineering principle by the year 2030. It wouldn't be in an airplane until 2050. So now the time horizon is going out to beyond 40 years from where we are today to be able to execute those things. If I take a look at where we've been with all this, it's been through a lot of rigorous reviews, and you can certainly, there's folks in my group who would be more than willing to come and talk about the details of this. But it's been through rigorous reviews, and so far there's not been a fatal flaw. If the engineering is the challenge, and we'll see whether or not at the end of the day that problem can be conquered or not. I think some people would argue that's been the problem with fusion power ever since the very, very beginning. But time will tell. We shall see. What about things that really go out of the box? Solar power. Well, water and wind, those are all kind of conventional things. But what about beyond that? Well, there's combustion things, right? We already alluded those. Biomass, et cetera. Nuclear fission and fusion. But what about some things that go really, really beyond that? Things like Casimir energy. Well, we know that it exists, right? Potential between two objects that are very close to one another. For any of those of you that ever worked in the world of MEMS, microelectromechanical systems, there's a phenomenon called stiction. Things just want to stick. It's probably what drives it. First they thought it was van der Waals forces, but it's not. Is there something in all this? I have no idea. Would I say absolutely there's no chance that it could ever happen? I don't think I would want to say that. Could it? It might. I have no idea. Well, let's look at the realm of all things nuclear. We're now out at a time horizon of 100 years. And I'm going to come back later and ground this in reality, lest you think I started drinking bourbon too early in the day. But look at, here you can see the energy density per unit mass. Well, hydrocarbon fuels, right? Hydrogen, we've already talked about hydrocarbons and hydrogen fuel. Skip over the one in the center just for a second. Fission, well, fission's a pretty well established. So hydrocarbons, not a problem. Hydrogen, well, it's got some engineering difficulties, but we sort of got that one straight. I didn't mention its use in fuel cells, for example. Ultimately, fuel cells run in hydrogen, so whether you reform the gas in a reformer, say methane, before it goes into a fuel cell, or you actually do it in situ in the fuel cell itself, you need to do that. Fission, that's pretty well established. Fission's been around as a controlled energy source since the 1950s. The Peach Bottom plant went online in the mid-1950s, and nuclear power has been on the grid, still produces 20% of the electrical power in the U.S. today. Well, fusion, well, we certainly don't know how to make, we know how to make big bangs with fusion at this point. We still haven't been able to control it as an energy source, but as I said, maybe we're only a few decades away from that. You go way out, you can clearly demonstrate, people have done it with antiprotons. Like you can generate, there is such a thing called antimatter. How you generate it, How you ever would put it into a reactor to react with matter, I have no idea. Nor does anyone else. But the basic physics we know exist. And what about the one in the very middle? Nuclear isomers. Well, nuclear isomers are known to exist. There are atoms of certain elements that can go into interesting momentum spin states. What people have never figured out how to do is how to actually extract the energy in either a controlled or uncontrolled way. Excuse me. But the appealing thing to isomers, if you look at them, energy density that's only a little bit less than that of fission power, but it doesn't produce nuclear waste the same way that a fission reaction would. There are no daughter products. You're not transmuting any elements to anything else. You're just changing a spin state, for example, in that atom and extracting energy out of it. Once again, we know they exist. No idea how to make them in large quantities. No idea to know how to get the energy out of the system at the end. But nevertheless, every single thing that's up there, whether it's a chemical-based source, like on the left, or it's a physics-based source from the middle over to the right, they're all real. It's just a matter of whether or not, from an engineering perspective, we can actually learn how to capitalize on them. Warp drive. Well, just think about it. There are all kinds of fields in the universe. There's gravitational fields, there's electromagnetic fields. Is there some way to take one of those energy sources and somehow warp a gravitational field? I don't know. I have no idea. Would I tell you that it's not going to happen in the next 200 years? Anybody in the room would bet that it's not going to happen in 200 years? Bet your life on it? I bet not. Nobody in this room knows how to do it. And certainly there's some underlying physics that say we ought to be able to do it, but we don't even know where to start with all that. But certainly it's a possibility as we really get long term. Well, here's a good example of not knowing what on earth is going on in the universe. This is just some scribbling equations that are the standard model, for which there are 19 empirically determined parameters to try to understand particle physics. And by the way, we can't rationalize it with relativity. And oh, by the way, not only can we not rationalize it with relativity, but it doesn't account for the fact that only about 5% of the universe is matter as we know it. There's dark energy and there's dark matter, whatever they are. So clearly, lots of things in the universe that make absolutely no sense. But if you talk to the astrophysicists and they talk about the rate of expansion of the universe, the mass of the universe, something doesn't work right. There's got to be more mass there than we actually can see. That's where the notion of dark matter has come from. There's something out there that's influencing gravitational fields. So our understanding of the basic physics of the universe, as smart as we think that we are, our understanding of the basic physics of the universe is still really, really quite primitive. And could there be something there over the course of the next 100 years? Maybe there will be. Maybe there won't be. But lest you think I'm totally nuts, just go back and look at what's happened over the course of the last decade, or last 100 years or so. 1862 is about the time that the first locomotive that was steam-powered hit 100 miles an hour. 100 years later, 1962, the J-58 pushed an SR-71 to Mach 3.5. 100 miles an hour to Mach 3.5 in 100 years. So can you imagine, AIAA didn't exist, but maybe some precursor to ASME existed. Can you imagine standing in front of an audience like this in 1862 when a steam engine had just gone 100 miles an hour and predicting that you could go more than 2,000 miles an hour in 100 years? You'd thought the person was smoking something, right? It just really moves. Look down at the bottom, the telegraph, 1840s, the internet, depending when you want to pick the start date, 60s or 70s when Vint Cerf and the others did some of the original protocol work on it. So maybe it's 150 years. But from the telegraph to the modern internet in a period of 150 years. And once again, if you'd gone back to Morris and said, we're going to have an internet in 150 years, he'd have said, you're going to what? Or when we finally went to voice with Alexander Graham Bell 30 years later, if you would have said to him, we're going to have an internet. Or if you went to Marconi early in the 20th century, or with radio, and talked about the bursting out of wireless communications that we have today and all the frequencies that are used and all the things that are done wirelessly, you wouldn't believe you. So any area that you can think about, what's happened in 100 years. Oh, and finally, over at the lower right, what happens if somebody lost a limb 100 years ago during the Civil War? During the Civil War, that's 150 years, but during the Civil War, if someone had a bad injury, what did they do? They amputated a leg or an arm. And maybe you got a peg leg, or maybe you got a hook. That was it. And if you paid attention to it, some of the things that DARPA's funded now involving bionic prosthetic limbs, the first ones were kind of simple, right? They'd hook up you'd have an electromechanical hand, and they'd hook up the electrodes up to, say, your chest or the upper part of your arm. And eventually your brain learned how to just twitch little muscles in your upper arm or your chest that would produce electrical signal that would make the hand use. And the brain's very plastic, so it learned how to do that. Well, now, some of the most recent work, implant electrodes in your brain, put a cap on, and it reads your thoughts, and it moves the muscles. So 150 years from a hook or a peg leg to a cap in your brain controlling an electromechanical hand. So think long and hard before you say something's not possible over the course of 100 or 150 years. And beyond that, I would also submit to you, look at how fast technology is accelerating today compared to where it was in the past. If you've read about things like singularities and all that sort of thing that's happening, where how fast technology is advancing, and is it going to overrun mankind eventually? I don't know if it will or it won't. But if something could happen in 100 years between the late 1800s and the late 1900s, or 150 years, at the rate at which technology was growing, at the exponent that it was growing at during those 100 years, imagine where it might go over the course of the next 100 years or so. So I'd submit to you that these ideas, some that we've talked about, I don't have any idea how to do them, but they are not totally crazy, and they could completely revolutionize what looks like the aviation industry today as we go forward. So what are some of the challenges? Well, one of them is incrementalism. Oh, that's not possible. Let's just sort of do it a little step at a time. What about trying to travel really fast at hypersonic speeds? That's been around since there's a lot of us in this room who probably at some point worked on NASP or the Orient Express. Probably almost everybody in this room who's over 50 worked on NASP at some point in their career, right? What about the funding constraints? These things are expensive to do, right? The valley of death for technology and for manufacturing. It's interesting, there are a lot of things where you might get the technology, the TRL level, over a hump, be able to build something, but trying to actually manufacture it efficiently and reproducibly becomes really hard. We also have the issue of the time, the bureaucracy. I'll tell you an interesting story. We, like a lot of others, have been interested in potential supersonic passenger flight for some time. That's been a dream ever since. Think about the Concorde and Boeing's design at the time. It's something that people have thought about for decades. And eventually, the efficiencies in the case of the Concorde didn't pan out. There's issues with noise, et cetera. So there's been a lot of work trying to be done to change the shape of airplanes, a lot of work that NASA's funded trying to turn a sonic boom into a sonic rumble, potentially get it accepted, et cetera. So at one point, there was actually some interest from wealthy individuals happened to be the Middle East, about what happens if you could build a supersonic business jet for me? Could you do that? Yeah, it turns out we probably could. And the we is not Lockheed. The we is lots of organizations could come up with a design to do something like that. And so at the end of the day, they say, wait a minute, let me get this straight. I give you a couple $1 billion. You build the airplane. It does exactly what you say it's going to do, as fast as you say it's going to do it. But then at the end of the day, the FAA has to say it's okay? I don't think so. And it stopped. So that's not meant at all to be a criticism of the FAA. It's just simply a matter of the fact that, there are things that are in place that take certifications, and it takes time to do that, a lot longer than at times it has in the past. Finally, I noticed a typo in there that should have all been capitalized, but I think a lot of us have talked a lot about STEM education. and the pipeline of supply of engineers and scientists to make a lot of these crazy things that I've just talked about potentially come to reality. But those are all things that we face. And the one in some ways that I find the most frustrating is the top one, incrementalism. People say it's not possible, you can't do that. And as a matter of fact, that's impossible doesn't start with things like a warp drive. That's impossible starts with people say you can't ever really make hydrogen work, or you can't ever really put a ceramic part in an engine, right? And we've already done that. So the incrementalism can really, really become lethal to an industry like this one. So where are we? Well, we've talked about some of the things that drive this, whether it's climate, environment, cost, et cetera. We talked about where we've been, from steam engines to jet engines to beyond. We've talked a bit about the challenges. So where all this goes next, who knows? But I think there's no doubt in my mind that energy and its uses will be one of the big drivers in aviation over the course of the next 100 years. So with that, time for some questions or comments. And there's microphones that are in the aisle. If anyone has a question, we should use those so you can hear it. If you just scream it out, I'll just repeat it, though. Okay. All right. Rick.
To what extent will global competition, either national security related or otherwise, drive some of this innovation?
So Rick's question was, how will competition, whether it's on the military front or a commercial front, drive these innovations? Well, I think you could argue at the end of the day that competition is what drives everything out there. So the question I think will be for us in the U.S. is whether or not we have the resources to rise to the challenge to face that competition. But without competition, I think things just stall. So it's going to be very, very important. The question is whether or not you can finance your own ambitions. Yeah.
There was a point on one of your previous slides about the technology readiness level and the materials readiness level, valley of death, and you didn't go into that at all, and I'm very curious.
Okay, it was manufacturing valley of death, not materials.
Materials is, well, anyhow.
Anyway, and the whole point behind that is, okay, TRLs. TRLs, something that the DoD started, technology readiness level goes from 1 through 9. And it tells you how mature technology actually is along the way. And by the time something goes off into an engineering system, typically you want it to be like a TRL 6 or beyond. So it's relatively mature. It's not something you just had working on a bench top in a laboratory. The manufacturing readiness level is, I might, for example, have, and I'll pick a material example, composites. And maybe I pick a composite that you're going to do out of autoclave curing on, right? Well, it might turn out that I know exactly how to do that in the lab. I can reproduce it. I know exactly how to do it. I know the quality of the parts. It's a very mature technology. Now the question is, oops, so the TRL is high. But now the question is start making large numbers of these things very fast for a commercial airliner. And I don't know how to do the manufacturing flow, right? That's the MRL. And so MRL almost always lags behind the TRL to get something done because you got to know the technology is possible before you figure out how to put it into, say, mass production. So that's what MRL means relative to TRL.
But what's the valley of death?
The valley of death is the cost that it takes to get over that. So in any case, if I take, we'll pick TRL, right? In order for me to design something theoretically, build something on a bench top is not a great deal of money. Once it's perfected and in production, it's not a lot of money. It's trying to get it over that valley of death where the costs are extremely high. So if you take a look at the dollars that are spent per increments of evolution in one of these systems, at the center, trying to take it from a concept on a bench top to an actual engineered item you can put into a product is extremely expensive. And in a lot of cases, a company or whatever can't afford to go through that development phase and the project just dies. And that's called the valley of death.
Thank you.
Anything else? Or off to, yeah.
I just wondered, based on your whole quality drivers, et cetera, if that whole area of drones is something that's a good example of where opportunities are driving things, bureaucracy, something. Can you maybe comment on that particular
Well, drones, yeah, there's a couple of things I would say about drones in the context of this. First off is, most of those are electrically powered, right? They're unmanned. We can all go out and buy a little quadcopter and we can sort of go flying it around. So, relatively short periods of flight, and a very obvious place for electrical power to sort of make its entree. And I think we all know that. The regulations around the use of drones is one that I think a lot of people struggle with. Yeah, you can get into this whole debate about privacy, but that's really kind of an emotional thing. I won't even go into that space. But just from a say, a safety perspective, right now you're supposedly restricted to fly below 400 feet. If you're in a quote unquote a toy sort of thing. You go beyond that. I mean, I think you may have heard, I think it was last spring, there was a 737 on approach into Orlando or someplace in Florida. Somebody had a drone up at a couple thousand feet puttering around with it. And I don't think you want to get a drone. It was a fairly big drone, like sort of this big, right? I don't think you want that ingested into one of the engines on your 737 on the way in. So the biggest issue with drones, I think from that perspective, is deconfliction of the drone with where commercial, military, and private aircraft fly. And whether it's ingestion into an engine or not, I think you've even seen pictures of birds that have gone through. There have been private pilots killed and military pilots by a bird strike where the bird goes through the windshield or the canopy and hits the person on the inside. And so if a 5-pound pigeon or whatever it weighs is going to go through and do that, you can imagine being a drone, what it would do if it hit that. So I think that deconfliction of aerospace will be the biggest issue. And that's what the FAA is really, really struggling with at this point in time. But it's a great test bed for a lot of these energy things that we've talked about, the simple ones. Yeah.
What do you think of complexity as a challenge for the future? I mean, the original jet engines, probably one person could understand, how a jet engine worked and all the parts in it. Now, it's incredibly complex and takes a huge team of people to put them together. And in the future, it seems like a lot of these technologies like fusion and whatever are just more and more complex.
Right.
Is there some limit to it that, some things get so complex that it's hard to build anything?
Well, it's certainly the complexity gets beyond the grasp of one individual person. I think there's no doubt about that. And just in a good example, if you take a look at an F-35, when that gets to full production, to be maybe 70 airplanes a year or so. Now, that's not that we couldn't build more than that. It's just that's probably what the order rate will be. But you take a look at the complexity of an F-35, 20 plus million lines of code that are in it, et cetera, and how long it takes to do one of those. We can still do more than one of those a week, even today. But you go back to World War II, the Willow Run plant in Michigan that Ford had that was building B-24s, one B-24 came out of that plant every 55 minutes. How'd they do that? For exactly the reason that you cite. A B-24 might have been a complicated airplane in 1943, but by today's standards, it wasn't. So I think we've also gotten to the point where you can go back and look in the early days of a Lockheed and say, well, geez, like the P-80. Kelly Johnson designed that whole thing himself just about. Probably true. Could somebody do that with an airplane today? Not a chance. So it's an issue now of how can you get teams of humans to work together with computational aids and tools to be able to attack and solve problems that are just more and more and more complex. And are we going to get to the point where somehow the limitations of our own ability as humans to think and to communicate, we run into a wall? We might. But there's no doubt that ever-increasing complexity is one of the reasons a lot of these things slow down. People like to criticize how long it takes to come out with a new commercial airplane or a new military airplane. A lot of that's driven by the complexity from one end to the other.
Thank you.
Okay, I guess time for people to go to other sessions, right, Rick?